Continuity is really just the idea of being able to trace a graph without picking up your pencil. It's sort of an intuitive definition, but we're going to move into a more formal definition using limits. If you look at the examples here, I can trace this entire graph without picking up my pencil. It is continuous across the x-axis. However, looking at the second graph, when I get to point A, I have to pick up my pencil to move across, and likewise, when I get to point B, I have to pick up my pencil again. So it's discontinuous at both A and B. While this is an intuitive definition, a more formal definition follows using limits. Note there are three criteria listed here, and for a function to be continuous, all three of these conditions must be true. F of A must exist. This means that the function must be defined at A, or must have a value. The limit of f of x at the point A, as x approaches A, has to exist. It can't go to infinity. And the limit of f of x has to equal f of A. If it does not meet one of these three conditions, then it's not continuous at the point x equals A. So in order to show that a function is continuous, we must show all three of these criteria are true. There are several ways discontinuity can exist, and I want to look at those. Notice here, this function is continuous. You can see that the limit from both directions equals f of A. The function itself equals f of A at that point, so it is continuous. In contrast, the second graph has a hole at A, and the difference is while the limit does reach the same point, the function itself does not equal that limit. So when the limit does not equal the same value as the function at that point, it is discontinuous, and this is a removable discontinuity. Here we also have a hole in the graph. Notice that the limit equals L, but the function itself, f of A, does not equal L. It's not defined at that point. Again, it is a hole and is removable. Another option for discontinuity is called a jump discontinuity. And in a jump discontinuity, you'll notice that the limit from the left does not equal the limit of the right, or it can be simplified to say that the limit itself does not exist as x approaches A. And finally, we see here that the limit of the function approaches positive infinity, so it does not reach a real number, and thus the function is discontinuous. And this is called an infinite discontinuity. One of the other things we want to be able to do is prove if the function is continuous. So let's consider an example here. We want to determine if the following function is continuous at x equals 2 and at x equals 3. To do this, we need to show the value of the function, and we need to show that the limit exists and is equal to the value of the function. So let's start with 2. If I plug in f of 2 into this function, I get 2 squared minus 2 minus 6 over 2 minus 3, which gives me a value of 4 for the function. So in other words, we can say that f of A exists, meeting criteria 1. The second criteria is we have to show that the limit exists and is a real number. So the limit of f of x as x approaches 2, notice if I plug that in, I get the limit. I can factor the top. Notice these are both going to cancel, which then leaves me with a polynomial. So I can plug in 2 to the function, and I get that the limit is 4. My final step is to show that the limit equals the value of the function. And since they are both 4, this is a true statement, and the function is continuous at 2. If we look at 3, we are going to show the same steps, but when we plug in 3, notice that we get x my x squared minus x minus 6, which is going to give us 3 squared minus 3 minus 6, and then the bottom is 3 minus 3. This gives us something undefined. So since the function itself is not defined, we have violated the first condition of continuity. And as you can see here, there is a hole there in the graph, so the function is discontinuous. A second example of showing continuity or lack of continuity is, suppose we look at an absolute value function. If we want to show if it is continuous at 0, the first thing we're going to do is simply plug in 0 to the function. And when we do, we get the absolute value of 0 over 0, which is not defined. And so therefore the function cannot be continuous. If we look at the graph, you're going to see here that this has a jump continuity. Note, to be discontinuous, there only needs to be one point where the function is discontinuous. It doesn't have to occur more than one place. And lastly, we're going to look at an example where we can help keep a function continuous. For example, in this one, we want to determine a value of k so that this function is continuous at 2. You can see that it's a piecewise function where 2 is going to be the issue. And in order for it to be continuous, we need to make sure that the right hand and the left hand limit will be equal to each other, and that the function will equal the value of the function and the value of the limit will be the same. To do this, we set the two pieces of the piecewise function equal, and then we want to find this continuity at 2. So plugging in 2, we get 2 squared equals negative 3 times 2 plus k, which gives us 4 equals negative 6 plus k. And solving for k, we get a value of k being 10.